Hello students, I am Azizi, Professor Electronics. In our previous session, we have learned that how to read the memory location from the microcontroller. In this session, we will learn that how to monitor and control the status of the port of the microcontroller, that is AT89C51 microcontroller, or any member of the MCS 51 family. In our previous session, we have written a program to read the value of the counter from the microcontroller. In this session, we will write a program to read the status of the switches connected on port 1 of the microcontroller, that is from port 1.4 to port 1.7. And we'll also write a program to control the status of the LEDs connected on port 1 of the microcontroller, that is from port 1.0 to port 1.3. So let's start our today's session. And here we can find the circuit of the microcontroller which we have developed in our previous session, that is AT89C51 microcontroller. In our previous session, we have connected 4 LEDs with the microcontroller, that is from port 1.0 to port 1.3. And we have connected 4 switches with the microcontroller, that is from port 1.4 to 1.7. And here we can find the counter value on the LCD, that is 000, and we have written a program in our previous session to read the value of the counter over serial link. And in our previous session, we have sent a command from the hyperterminal of the micro C to read the value of the counter from the microcontroller, and we had established the link between the microcontroller and the USR terminal of the micro C using a virtual serial port emulator. So let's observe the command for the serial communication which we have developed in our previous session to read the value of the counter from the microcontroller, to read the status of the switches from the microcontroller, and to control the status of the LEDs. And here we can find different commands for the serial communication which we have developed in our previous session. To read the value of the counter, we have written a command, that is $send counter and the hash. And to read the status of the switches, we have written a command, that is $send switches and hash. And to control the status of the 4 LEDs connected on port 1, we have written 8 commands, that is $set LED1 and hash to set the LED 1, and clear LED 1 and hash to clear the LED 1. Similarly, we have written the other commands, that is set LED 2, clear LED 2, set LED 3, clear LED 3, set LED 4 and clear LED 4. And now we'll send the command to the microcontroller, that is send counter and hash, and we will observe the result of our previous program. And here we can find virtual serial port driver, and we have configured 2 ports, that is COM port 2 and COM port 3. Now we will use these virtual serial ports to communicate between microcontroller and the hyperterminal of the micro C. And here we can find we have assigned the COM port 2 to the microcontroller with a baud rate of 2400, that is 2400 bits per second. Okay. And here we can find the USR terminal of the micro C Pro for AT51 compiler. And here we can find we have assigned the COM port 3 to the USR terminal of the micro C, and the baud rate is 2400 bits per second, and the data format is ASCII characters. And now we'll connect the COM port 3, and now we'll send the command to the microcontroller, that is $SND CNT and hash. Okay, send. And here we can find 3 characters, that is 000. It means the value of the counter is 0. And now we will run the counter in Proteus simulator. And now we will run the counter by pressing switch 1. Here we can check the counter is incrementing. And now we will stop the counter. And we will check the value of the counter on the USR terminal of the micro C. Okay, clear. And we will send the command once again. Okay, send. And here we can find the value of the counter is 7. And here we can find the value of the counter is 7 in microcontroller. And now we will modify our previously written program to read the status of the switches connected on port 1.4, 1.5, 1.6 and 1.7. And now we will read the command, that is send switch in the microcontroller to send the status of the switches to the USR terminal. So we will implement the command, that is $SND SWH and hash. And here we can find our previously written program, that is serial communication project. And here we can find the directives for our program, that is org00h, jump to initialization routine, org00bh, that is ljump timer 0 interrupt service routine, org0023h, ljump serial interrupt service routine, and org30h. And we have started writing our program from the 30h location, that is initialization routine. And here we can find we have initialized different special function registers of the microcontroller. We have moved the value, that is -13, to the timer 1 high to get the baud rate, that is 2400. And here we have modified the value of the T mode register, that is 21H, to configure the timer 0 in 16-bit timer mode, and to configure the timer 1 in 8-bit auto reload mode. And here we can find the interrupt enable register, and we have moved the value that is 92H to enable the interrupt of timer 0, serial communication and global interrupt. So here we will write that is serial interrupt. It means we have enabled the bits that is timer 0, serial interrupt and global interrupt in interrupt enable register. And here we have moved the value that is 50H to the SCON register. And here we can find in SCON register we have set the value of the bit that is SM1, and we have cleared the status of the bit that is SM0, and we have set the status of the bit that is REN, receive enable, by setting the status of SM1 bit as 1 and setting the status of SM0 bit as 0. It means we want to use the UART of the MCS51 family as 8-bit UART mode, variable baud rate set by timer. So we have moved the value that is 50 to the SCON register, and here we can find our main routine, and we are calling 5 routines in our main program. That is go position, print message, print counter, call switch routine, send counter, and now we will add another subroutine in our main program, that is send switch status. So here we will write that is call SND underscore SW underscore STS, that is send switches status. And here after send counter value subroutine, we will write our new subroutine, that is send switches status routine. So here we will write SND underscore SW underscore STS using colon. And here in send switches status subroutine, first we will check the length of the message. So here we will write that is move accumulator comma MSG underscore LEN, that is move the value of the message length register to the accumulator. And here we will write that is compare jump not equal accumulator comma hash 8 comma send switch exit SND underscore SW underscore EXT. But if the value of the message length register will be 8, then our program will come to the next line. And here we will repeat the procedure that we have written in our previous session, and we will copy these lines from our previously written subroutine, that is from move accumulator receive register 0 to move message length, that is 00H, control C. And here we will paste these lines in our new subroutines, that is send switch status. So we'll paste these lines here, control V, and here we will check if the value of the receive register 0 will be $, and the value of the receive register 7 will be hash. Then we'll check if the value of the receive register 1 is S, and the value of the receive register 2 is N, and the value of the receive register 3 is D. But here we will check if the value of the receive register 4 is S, and here we will check if the value of the receive register 5 is W. So we'll replace this letter, that is N, with W, and we'll check if the value of the receive register 6 is H. So we'll replace this letter, that is T, with H, and we'll also change the subroutine name, that is send counter exit, with the name that is send switch exit. So we'll copy this name from here, and we will replace these names, control V. If the all 8 received characters will be matched with the characters, that is $hash SND SWH, then our program will come to the next line, and here we have reinitialized the value of the message length to the 00H, and now we'll write our program to send the value of the switches to the hyperterminal. So here we will write that is move accumulator comma port 1, as we have connected 4 switches to the port 1, that is from port 1.4 to 1.7. As the switches are connected with the higher nibble of the port 1, so we'll mask the lower nibble of the port 1. So here we will write that is ANL, that is AND logic, accumulator, comma 0F0H. So here we have masked the lower nibble of the port 1, and now we'll move the status of the all 4 switches to the lower nibble. So we'll swap the accumulator. So we'll use the instruction that is swap accumulator. So here we will write that is SWAP, that is swap accumulator. It means we have swapped the higher nibble with the lower nibble, And now we'll save the contents of the accumulator to the R1, that is the second register of the register bank. So here we will write that is move R1 comma A, and here we'll initialize the value of the R0 to the 00H. So here we will write that is move R0 comma hash 00H. As we have to send the status of the 4 switches to the hyperterminal, so here we'll assign the label to a routine, that is SND switch underscore BAK using colon, and here we will write that is move accumulator comma R1. We have moved the value of the R1 register to the accumulator, and here we will check all 4 bits one by one. So we'll end the accumulator with 01H to filter out the least significant bit. So here we will write that is ANL accumulator comma hash 01H, and here we can find all 4 switches are active low. It means if no switch will be pressed, then the status of the port, that is from port 1.4 to 1.7, will be high, and here we will invert the status of the least significant bit. So we'll apply the XOR logic. So here we will write that is XRL accumulator comma hash 01H. It means if the status of the least significant bit will be 1, then the 0 value will be moved to the accumulator, and if the value of the least significant bit will be 0, then the value 1 will be moved to the accumulator. That's why we have applied the XOR logic, and now we will OR the value of the accumulator to convert this value into the equivalent ASCII character. So here we will write that is ORL accumulator comma hash 30H, and here we have converted the number into the equivalent ASCII number before sending the value to the hyperterminal. And now we'll move the value of the accumulator to the SBUF. So here we will write that is move SBUF comma A, and on next line we will wait for the complete transmission of the SBUF, and here we will write that is jump not bit TI, that is transmit interrupt, comma $. If the serial transmission will be completed, then the bit, that is TI, will be high and our program will come to the next line. And now we'll move the value of the R1 to the accumulator once again to check the status of the second bit. So here we will write that is move accumulator comma R1, and here we'll perform the operation, that is rotate right accumulator. So here we will write that is rotate right accumulator. It means we have moved the status of the second switch to the least significant bit position, and now we'll save the contents of the accumulator to the R1 once again. So here we will write that is move R1 comma A, as we have to repeat this procedure 4 times to send all 4 switches to the serial port. So here we will write that is compare jump not equal R0 comma hash 03H comma SND underscore NXT underscore SW. But if the value of the R0 will be equals to 3, then our program will come to the next line and will get exit from the subroutine. So here we will write that is send switch exit, Control C, Control V using colon, and here we will write that is return, and here after this line we will write the routine, that is send next switch. So here we will write that is send next switch, Control V using colon, and here we will write that is increment R0, and after incrementing the value of the R0 we will jump back to the routine, that is send switch back, and here we will write that is jump SND underscore SW underscore BAK, and here we have completed our subroutine, that is send switches status, and here we can find send switch STS, that is send switches status, and here we have moved the message line to the accumulator. And here we have checked if the length of the message is 8 character, then our program will come to the next line. And here we will check if the value of the receive register 0 is $, and the value of the receive register 7 is hash, then our program will check if the value of the receive register 1 is S, value of the receive register 2 is N, and the value of the receive register 3 is D. And here we will check if the value of the receive register 4 is S, then the value of the receive register 5 is W, and the value of the receive register 6 is H. Then our program will come to the next line and it will reinitialize the value of the message length to the 00H. And here we have moved the value of the port 1 to the accumulator, and we have masked the lower nibble of the accumulator by using the AND logic, that is AND accumulator with F0H. And here we have swapped the contents of the accumulator to make the higher nibble as lower nibble. And here we have saved the contents of the accumulator to the R1 register, and here we have initialized the register, that is R0 to the 00H. And here we have returned back the copy of the accumulator from the R1 to the accumulator. And here we have applied the AND logic with the accumulator with 01H to filter out the least significant bit. And here we have applied the XOR logic with the accumulator with 01H to invert the status of the least significant bit. And here we have applied the OR logic with the accumulator with 30H to convert the number into the equivalent ASCII number. And we have moved the value of the accumulator to the SBUF. And after moving the value of the accumulator to the SBUF, here we are waiting for the complete transmission of the SBUF. If the transmission will be completed, then our program will come to the next line, and here we will move the saved copy of the accumulator back to the accumulator. And here on next line we have rotate right the contents of the accumulator by 1 to shift the status of the next switch to the least significant bit. And we have saved the contents of the accumulator to the R1 register. And here we have compared the value of the R0 with 03H to repeat the operation 4 times. If the value of the R0 register is not equals to 3, then our program will jump to the routine, that is send next switch. And here we have the label, that is send next switch. And here we have written an instruction, that is increment R0. And after incrementing the value of the R0, our program will jump back to the routine, that is send switch back. And it will move the value of the R1 to the accumulator, which we have saved on this line, that is 368. And this operation will be repeated 4 times until the status of all 4 switches will be transmitted to the serial port. And now we'll compile our program and we'll check the result of our program on Proteus software. Okay, compile. 0 error, 0 warnings. As we have modified the same project, so there is no need to load the hex file once again. And now we will run the simulation. And here we can find the status of all 4 switches, that is from port 1.4 to 1.7 is high. If we press the any switch, the status will be low. Let's check. Here we can check port 1.4 is low now, port 1.5, 1.6 and 1.7. And now we will run the counter by pressing the switch 1. And now we'll stop the counter. And now we'll send the command to read the value of the counter from the USR terminal. And we will also send the command to read the status of the all 4 switches. And now we will connect the COM port 3. Okay, connect, clear. We'll send the command, that is $SND, CNT and hash. Okay, send. Here we can find the value of the counter is 8. And here we can check the value of the counter is 8. And now we'll send the command to read the status of all 4 switches. And here we can check the command, that is $send switch and hash. And here we will change the command, that is send switch. So here we will write that is SWH. And we'll send the command to the microcontroller. Okay, send. And here we can find the status of all 4 switches that we have received on hyperterminal is high. But according to the logic that we have written in our program, the status of the all switches must be 0, 0, 0 if all switches will be high. And now we'll change the status of the first switch that we have connected on port 1.4. And here we will change the status of the switch connected on port 1.4. Now the status of the port 1.4 is 0. And we will read the status of all 4 switches on USR terminal once again. We will send the command once again. And here we can find no change in the status of the switches. Let's check where is the error in our program. And here we can find on line number 356, we have used an AND logic with the accumulator with F0H, but here we have missed the character, that is hash. So here we'll write the character, that is hash. And now we'll compile our program once again. And now we will run the simulation once again. And here we can find the status of all 4 switches is high. And now we'll read the status of all 4 switches on USR terminal. And now we will send the command, that is send switches once again. OK, send. Here we can check the status of all 4 switches is 0 now. And now we will set the status of the first switch, which is connected on port 1.4. We will set the status of the switch connected on port 1.4 as low. And here we can find the status of the switch connected on port 1.4 is low. And now we will read the status of the switches once again. And we'll send the command once again. OK, send. Here we can check the status of the switch connected on port 1.4 is 1 now. And now we'll press the second switch connected on port 1.5. And we will read the status of the switches once again. OK, send. And here we can find the status of the switches connected on port 1.4 and 1.5 is 1 now. And now we'll switch on the remaining 2 switches connected on port 1.6 and 1.7. And here we can find the status of all 4 switches connected on port 1.4, 1.5, 1.6 and 1.7 is low now. And we will read the status of the all 4 switches on the USR terminal once again. OK, send. Here we can find the status of all 4 switches is 1 now. Now we'll switch off all 4 switches connected on port 1.4, 1.5, 1.6 and 1.7. And we will read the status of all 4 switches once again on serial link. OK, send. And here we can find the status of all 4 switches is low now. It means all 4 switches are off. And here we can find we have received the command, that is $snd, swh and hash. In this session we have learned that how to read the status of the switches which are connected on port 1 of the microcontroller, that is from port 1.4, 1.5, 1.6 and 1.7. In our next session we will write a program to control the status of the LEDs connected on port 1, that is from port 1.0, 1.1, 1.2 and 1.3. OK, see you in next session with a new program. Thanks for watching this semi-language programming course. We hope that you find this course very helpful to learn semi-language programming. If you feel that this course contributes and enhances your embedded system design knowledge, then go ahead and hit like, share and subscribe buttons. And do not forget to press bell icon to stay updated with every new upcoming video from Electroeducators as soon as it goes up. Electroeducators also offers technical consultancy in following fields. For assistance regarding technical problems, projects and any consultancy, feel free to reach out at our email address electroeducators@gmail.com. Okay, see you in next lecture.